Hello, let's go ahead and get started here on a lecture, another one on area, but this time we're going to be talking about the area between curves. So as I mentioned last time, we're going to have a slight difference in how these problems are worded, but it should be pretty clear. On the past problems when we were asking for area, we were just talking about space occupied. And in that scenario, we were generally dealing with just a single function and looking at its area that is occupied between that function and the x-axis. We didn't care about positive or negative. We didn't care about above or below the axis. But here, we're going to be talking about having two different functions, two different curves, and we're going to actually worry about the area between them. And so let's go ahead and go on to sort of an example here where we can build up how to do this. So we'll start off here. And so starting off, we're going to talk about the two functions here. And I actually am not going to label these specifically, but these functions are going to be f of x and g of x. So those are my two functions, f and g. One of them is red, one of them is blue. We'll see why later. I don't want to actually specify. But we've got a red function and a blue function. And in this case, they look pretty similar. All I did was I just took the same function, I just shifted it up and down a little bit. But regardless, they are two different functions. And so we can talk about the area between them. And if we're talking about the area between them, basically, we're going to have to designate an A and a B. So these are going to be our endpoints here. So we're just going to look here. So here's my A that goes up. That's kind of a barrier, a wall, if you will. There's the B. And then we're just going to look at the area all in here, all in there. And excuse a couple of those, me going outside the edges there. But we're going to look at this area all in between, all that green that's all in there. And we want to calculate that. So what we can do is we can actually figure out a couple different areas and use them together to actually find this area. So the first thing that we're going to do is we're going to find the area underneath the blue. And I've got that colored here in kind of this brown, beige, tan kind of color. And so what we should be able to figure out here is a formula for this area. And actually, this area, let's do a different color there. This area would be the integral from a to b of my function, let's just call it f, dx. We have a formula for that area. We've seen that definite integrals represent the area underneath a curve between 2 points. And so we've got that right here. We've got a formula right there. And with that, I guess for now, I'll go ahead and label this as f and I'll label this as g. We'll talk about later why we got to be careful with that. But for now, we've got this formula here for the brown area, that tan area. And so we've got an area underneath the blue. Likewise, we could actually talk about an area underneath the red function. And again, let's go ahead and call this red function g like we did on the last slide, and this blue function f. And so we've got an area here, and I'm gonna write this big just so we make sure that we understand that it covers the entire area there. It's all of that green. It's everything underneath the red. So what we can do is we actually have two different formulas, two different integrals for each of these areas, the area under the red and the area under the blue. So what we can do, and watch the colors here, we can actually separate these. And if we want to find just this inner area in the middle here, this pinkish color, what we could do is we could take the area underneath the red. We could take both the pink and this beige, this brown color. We could take both of those together and we can just subtract off this beige brown color. And that just gives us the pink right here. So luckily, what we have to sort of write out a formula with the colors, pink plus, we'll keep calling this brown, that's actually equal to the green that we had before. These two colors together are this entire green. So we have a formula here. We know that this entire green is given by this integral of g. And so that's what this pink and the brown are. So all we have to do is basically we have to take the integral underneath G and we have to subtract the integral underneath F. And so what we'll see here is that if we take the integral from A to B of G of X, remember, that's going to be this entire region here. That's what we had all highlighted in the green before. And then we split it into those multiple colors. So we've got this entire area here in this integral of G of X. And then I want to just subtract off this bottom portion, which is just the integral of F of X. And we've seen that before on the past slides. So we're going to subtract off integral from A to B of F of X dx. And now the great thing here is that we actually have a formula here that we can simplify, and then it gives us an even simpler formula for finding the area between these curves. We can use our integral properties. So we've got the integral from A to B of G of X dx minus the integral of A to B of F of X dx. We can actually simplify these because the limits of integration are the same. We can use those integral properties to write this as G of X minus F of X. And there we go. We've got a nice formula for the area between these curves. So we see this right here. We've got our graph. We've got that pink area there. We realize that it's the area here minus the area here. What you might notice is that here I've written F minus G. And back here I wrote G minus F. So the question there is, what the heck is the difference here? Why am I writing G minus F in one spot, but then F minus G in another? Well, the reason is because the naming of F and G was completely arbitrary. There was no reason for me to necessarily name the red function G of X and the blue function F of X. I could have flipped these if I wanted to. And so really what we see here is that the naming of our functions is not really important. We just want to make sure that we're always doing what I'll write out as top and bottom. So we'll make sure that we're always doing top minus bottom here. We want to make sure that when we do these integrals that we actually have to deal with what's on the top and what's on the bottom there. So the naming of F and G isn't that important. Be careful because sometimes in problems you'll see F and G will be labeled just to give our functions nice, neat labels. So this formula may not directly apply. It might not be exactly whatever F is listed at minus exactly whatever G is listed at. In general, it's top minus bottom, but we kind of have to generalize it. We have to give it some sort of naming. So in this formula, we say F minus G, but it very well could be G minus F instead, depending on which function is on the top and which function is on the bottom. So you'll notice here that I've said this is when the curves don't intersect. Well, if the curves do intersect, and you'll notice I've changed these functions just a little bit here. If these curves actually intersect, and here I've made them intersect perfectly at A and B, generally what you'd have to do is you'd have to find these intersection points. You'd actually have to go about algebraically finding those. And once you have that, then you know what A and B are. You can set up your integral, and it's the exact same thing. It's top minus bottom. Right there. So top minus bottom. Now, this could lead to a question. You might ask, well, what if we have a function or two functions rather that look like this? What if we have a function that goes like that? And then what if we have a function that goes like this? Ooh, let's do a different color there. And so if we're looking here for the area between these curves, you'll notice that this area is encompassed in two different regions, right in there and right in there. Both of those greens are each areas between the curves. So we got to be careful here. And when we deal with this top minus bottom, you'll notice that right there at that point, the top minus bottom change, or the top and the bottom change. To the left of this point, let's go ahead and give ourselves some labels. Let's say A, B, and C. Let's label G of X. Let's also label F of X. And so right at that point, X equals B, we'll notice that the top and the bottom actually change. And so when we have that, we need to make sure that we actually split our integral up accordingly. So for this area, let's go ahead and label area in the green here. We'll label area in the yellow here. So when we've got those areas there, we can actually come up with a formula for each of these. Let's go ahead and move these down a little bit. Give myself some more space. So we've got that. So our areas here in the green, we're going to look at top minus bottom. We're going to say, all right, in the green area, f of x is on top. So I want to do an integral from a to b of f minus g. And I'm going to leave out the of x notation. We understand their functions, f and g. So we're just going to do that subtraction. And then there we go. We're integrating from a to b. But in the yellow here, we'll notice that it changes. And so we're going to integrate from b to c. Those are our endpoints. We're going in this region here because that's our area right there. So we're going to integrate from b to c. And in this case, we're going to actually have to do top, which is g, minus bottom, which is f. So we're going to then, once we do each of these green and yellow integrals, we're going to have to actually add them together, and that'll give us the area in between these functions. So sometimes we have to be careful about which is top, which is bottom, and sometimes it can change here. And most of the time, you're not actually given these values. You actually have to find these values of a, b, and c by doing some algebra and finding points of intersection between f and g. So got to be careful when those curves intersect. Let's go ahead and do an example here. So what I'm gonna do here is I'm gonna give you a problem. I'm gonna say, let's find the area bounded by, and then I'm gonna go ahead and list 4 functions here, or four things, I should say. So we'll have f of x is negative x squared plus 1. G of x is going to be equal to 2x plus 4. So we've got a parabola and a line. And then I'm also going to say, hey, let's look at the line x equals negative 1. And let's look at the line x equals 2. And so there's a couple things we got to be careful about here. First, we always want to remind ourselves that the fact that this polynomial is f and this line is g doesn't really mean anything. I could switch these letters and it wouldn't change our answer. So f and g aren't really important as to which is which. And then the second thing we got to keep in mind is, are these vertical lines or are they horizontal lines? And this is easy to get yourself sort of mixed up on them. But if we're saying that x is equal to negative 1, that means the x coordinate is always negative 1, and I am free to move in the y coordinate, which means if I'm set on my x and I'm free to move in the y is vertical, that's up and down. That is a straight line up and down. That is a vertical line. So both of these are vertical lines, so we'll keep that in mind. And what we need to do here is we actually need to graph these. You might just guess and get lucky as to which one of these functions is on the top and the bottom, but that is not a surefire way of doing this because, well, you're just guessing. And so if you want to make sure that you know for a fact which function is on the top and which function is on the bottom, we have to graph. So just to save some time here, I've actually graphed these using an online graphing calculator. And what we've got here is we've got our line, and I'll go ahead and label this here. So we've got g of x is equal to 2x plus 4. We'll note the y-intercept at 4 right there. And then we will note the slope of 2. As I move over 1, I've gone up 2 right there. And you can see that with these labels of 1 and 6. So we've got that line right there. Let's go ahead, let's label this y and x. So we've got that. And now in the blue, we've got our f of x is equal to negative x squared plus 1. And so I see this as a parabola, but it is negative x squared. So instead of facing up, it's going to face down. So negative x squared is going to look like that. But then because I add 1, I just take this guy and I shift it right up. And so we're right there, and we have our parabola right there. You using this parabola, you can figure out some more values here. We'll note that this value might be important. This value might be important, this and this. And so really what we've got here is we have an area that we can figure out, or excuse me, we have a region that we can figure out the area of. And I'll outline it here in the green. We've got all of this in the green in here that we want to find the area of. And so now we can very easily see where our top and our bottom are. We know that our line is the top and the parabola is the bottom. And in this case, they actually don't intersect. So it's a good thing that I gave us our x equals -1 and our x equals 2 vertical lines, because now we have those sort of endpoints, right? So if we're trying to find this area in here, oh, we'll leave that there. So if we're trying to find this area, then we need to do a top minus a bottom, and we're gonna have to take an integral. So let's go ahead and do that. And recall, keep this in mind, I'm gonna move on to the next slide here. Keep in mind the top being the line and the bottom being the parabola. So when we do our integral, we're gonna say integral from a to b. In this case, it's g of x minus f of x. Remember, that could be f minus g in other problems, but here, as we've labeled them, it's g minus f. A and b, those are our endpoints, and as we said, we've got that right there at -1, and we've got that there at 2. So we've got the integral from -1 to 2 of g, which was the line, minus f, which was the parabola. So at this point here, we can just continue on. We'll do some simplification. And here we've got 2x plus 4 plus x squared minus 1. So just rewriting this and making it look a little bit nicer. And now this is a simple integral. At this point, we've got simple power rule application here. We could go on and we could evaluate this. I'm not going to bother with that right now, but we can actually take this here. We've got our x squared plus 2x plus 3. We'll do a power rule on each of these terms. We'll evaluate at 2 and -1 and subtract those. And that's just doing our good old definite integral calculations there. And so at this point here, we're basically done. We would end up with some specific answer here. And it'd be a numerical answer, and that would be the area in this green represented right there in that outline. And so this is a fairly simple problem. All we had to do was graph. We had to figure out which one was top, which one was bottom. The functions never intersected. And so it was lucky that we were given those other points there, those other end values, because those were our limits of integration. And then we just set up our integral and we evaluated it. If this line were maybe a little different, if this line went more something like this, then you're going to have to be careful there, because now you can see that and let me go ahead and redo that. So if our line went something like this instead, now you can see that here the top and the bottom change from here and over here. So the top and the bottom would change if we had some intersection that was in the middle of this region here. If we had intersection inside these bars here, then we'd have to be more careful. But in this case, we don't. Fairly straightforward example. So there we go. We've got our integral set up. That's the area between curves. and we'll go ahead and call that the lecture.